Now let's take a look at some radiometric concepts that are particularly useful for understanding image intensities. Let's start with the simplest of them all, an angle in 2D. You all know the definition of an angle in 2D. You have a circle here of radius r, and you have an arc shown right here, and we want to know what is the angle subtended by this arc as seen from the center. That angle is d theta, and that's equal to the length of the arc dl divided by the radius r. It's a definition of an angle. And the unit is radians. Turns out that this is actually a dimensionless quantity because you have d distance divided by distance, but we give it a name, radians, because we want to distinguish it with respect to other dimensionless quantities. So that's an angle in 2D. Now we can talk about what we mean by an angle in 3D. So in this case, you have a point right here, and this point, let's say, is looking at this infinitesimally small area, dA, and we want to know what is the angle in 3D, called the solid angle, subtended by this area. So we take the area, and we compute what's called the foreshortened area, which is dA prime. dA prime is dA cosine theta, where theta is this angle right here. That's this area, dA prime. dA prime divided by r squared is the solid angle d omega. So d omega is equal to dA cosine theta divided by r squared. The unit in this case is steradians. Again, it's a dimensionless quantity. Now, here you have an infinitesimally small area, and so this definition holds. If you want to actually find the solid angle subtended by a large area on the sphere, which lies within the solid angle, you need to find the area of the spherical cap that lies within that solid angle. So you have to integrate this over that area and then divide by r squared. It turns out that the solid angle subtended by a hemisphere is 2 pi. Sphere is 4 pi. Okay, so with that in place, now we can start talking about the radiometric concepts that are of interest to us. Let's start with light flux. So you have a light source here which is illuminating the surface, and the light flux is nothing but the power emitted by the source within a solid angle. So if you take this solid angle here, which is d omega, then we can say that the flux that is emitted within d omega is d phi, and that's expressed in terms of watts. That's the unit of flux. And with that in place, we can talk about the brightness of a point light source. This is a light source right here, and its brightness is called its radiant intensity. We'll denote it as J. The radiant intensity is the flux emitted by the source per unit solid angle. So it's d phi divided by d omega, and the unit is watts per steradian. And so now we can talk about the illumination of a surface. So you have the brightness of a point light source, and it is at some distance from the surface right here. Distance is r. And the question we're asking is, what is the illumination of the surface? The illumination of the surface is called surface irradiance. Surface irradiance, and that's denoted by E. And that is the flux falling on the surface per unit area of the surface. d phi by dA, and the unit is watts per meter squared. And so if you have a source with radiant intensity J, we can now calculate what the irradiance of the surface is going to be due to that source. That's going to be J, the radiant intensity of the source, times d omega, because that gives us d phi, divided by dA. But we know what d omega is for this particular case. That's equal to dA cosine theta divided by r squared. So you end up getting J cosine theta divided by r squared. So let's take a look at this for a second. It says that the strength of illumination of a surface, which is the surface irradiance, of course, is related to the brightness or the radiant intensity of the source, and it is 1 over r squared, the distance between the source and the surface itself. That's called the 1 over r squared fall off, meaning that as you increase the distance of the point light source from the surface, the illumination of the surface is going to fall as r squared, times cosine theta, which is cosine of the angle between the direction of the light source and the surface orientation right here. So when you're right on top of the surface, your irradiance is going to be maximum because it's going to be cosine 0 equal to 1. But as you go off towards the grazing angle, it's going to fall to 0. Okay, so now we can talk about the brightness of a surface itself. The brightness of a surface is defined as its surface radiance. This is a little bit more of a complicated concept. How do you measure the brightness of a surface? So imagine that this is the surface right here, and you want to measure the brightness of the surface. You're going to use a sensor to do this. And let's say the sensor has some area. This is a little ring right here, that's your sensor. If you place the sensor right here, it's going to collect light from the surface. You can see that if you move the sensor back, it's going to receive less light from the surface because the solid angle with respect to each point on the surface reduces as you move further away. And also the second thing that influences this measurement is that if I increase the area of the surface, you're going to get more light entering this sensor, and therefore the brightness is going to increase. So somehow when you define the brightness of a surface, you need to normalize with respect to both the area of the surface as well as the solid angle subtended by each point on the surface with respect to your sensor itself. So that brings us to the definition. Radiance is defined as the flux per unit foreshortened area per unit solid angle. So it is the flux received by the sensor per solid angle per unit foreshortened area. We use the foreshortened area in this case because we want to accommodate for the fact that the area as seen from the sensor is really the foreshortened area. So that's the definition of radiance, and that is watts per meter squared per steradian. So this radiance is a very important quantity, and it has the following properties, which is that the radiance depends on the direction that you're looking at the surface from. That's theta r right here. Depends on theta r. And the surface, of course, can radiate in all directions. And then finally, the radiance depends on the reflectance properties of the surface, that is, the material properties. The ability of the surface to take light from the light source from this direction and scatter it or reflect it in the direction of observation.